And this is something called the node rule. But it's really just an expression of conservation of charge plus the fact that we're in a steady state. Okay. You could think of this as sort of a conservation of current rule in that sense. And the node rule simply says that in the steady state, the current in has to be equal to a current out of a node. What's a node? Well, a node is just a point or any specific spot in the circuit. So if I choose this light bulb as the node that I'm interested in, then the current flowing into that node, the electrons per second flowing into that node, have got to be equal to the number of electrons per second flowing out of that node at any given time. Okay. The number of electrons flowing out of the battery per second has got to be equal to the number of electrons flowing into the battery at any given time. The number of electrons flowing into point B has to be equal to the number flowing out of point B at any given time. Okay, so that's a node is just a spot in the circuit. And we'll deal with more complicated circuits later, but it also has consequences if you have a more complicated circuit where the wires actually branch apart. So, for example, if you have a battery here and some circuit that looks like this, okay, and it comes back together maybe over here. So here is the flow of electrons coming out of the battery. We'll call that I1. And then here's a spot where you have two branches in the circuit, and here's I2 and I3. And so by the node rule, what has to be true? Okay, they just split. What has to be true about the relationship between these three currents? I1 is equal to I2 plus I3, right? Pick that as the node. The total number of electrons flowing in has got to be equal to the total number of electrons flowing out per second. I2 plus I3 is the total current out. I1 is the total current in. Okay, so it works in more complicated situations as well. Now, those of you, it's natural to think that the current in is greater than the current out. This is actually a common first guess, and it's kind of a natural one to make because you think that something is being used up, right? The light bulb's giving off light. Well, it's not the current that's being used up. What is being used up, or in some sense? Okay, energy, right? Where energy is being given off in the form of light. What's delivering the energy to? The battery, right? The battery is a source of energy here. The battery is doing work, and we'll quantify that next time or next week. But so we're not getting something for nothing. Okay, we are converting energy stored in the battery into light that's being given off, but it's not the current that's being used up. Okay. Questions here? This is one of the central ideas of this chapter is this node rule, where we're going to be using it over and over again in different applications. So, yes. Okay, so you're talking about the drift speed, right? Let's continue on, and I'll come back to that. Okay, so let's think about this. Well, in fact, okay, let's look at this situation. Here is let's draw that circuit again. So here's the battery, and here's the light bulb. Let's assume that it's the same type of wire throughout the entire circuit, right? So the wire here has some electron density N, and it has some electron mobility U, okay? It's copper or something, so we can look those up in a table or something and find out what they are. So we can say that, okay, the current at A is equal to the current at B. I also know that I is equal to NA V, right? So let me plug this in. The electron density at A times the area of the wire at A times the velocity of the electrons at A is equal to the electron density at B times the area of the wire at B times the electron drift speed at B. Okay? What's the same on those sides, on those equations, or on both sides of that equation? Okay, the area is the same. It's the same thickness of wire, we're assuming. So they would cancel out on both sides. And n is the same, right? The number of electrons per unit volume is the same because it's the same material. Copper, for example, on both sides. So what we find is that, in fact, the drift speed in this particular case turns out to be the same as well. If you have the same thickness of the wire and the same number of electrons per unit volume, then for the currents to be the same, you have to have them moving at the same speeds too. So that's a good question. Other questions here? Well, let's change it up a little bit. What if we have a circuit where we have a thick wire and a thin wire, okay, just connected in series with the battery, and A1 is bigger than A2. It's the same material, so the density of electrons is the same, the mobility of the electrons is the same. What do we know about the currents in wire 1 versus wire 2? Well, it sure is tempting to say that the currents are different, right? Because we have this thick wire here, which obviously has to have more electrons in it flowing past at a higher rate. But what do we just say about the node rule? Current in is equal to the current out, right? So pick that as the node. The junction between the two wires is a node, for example. So the node rule says that the number of electrons flowing in has got to be per second has got to be equal to the number of electrons flowing out per second. Go ahead. Okay, so so we know that the currents are equal. What about the drift speeds? What about the drift speeds? Sure, the area is bigger. So the number of electrons per second has got to be the same in wire, well, we call them 1 and 2 now, wire 1 versus wire 2. Okay, or if it weren't, you'd have charge building up at that node, right? And you wouldn't have a steady state. You'd have something changing where the charge keeps building up. So let's follow your nose here. What's going to be true about the drift speed in this case? Yeah. Okay, so we're starting to get the idea, right? The velocities are different, and the drift speed in wire number 2, the thinner wire, has got to be bigger than the drift speed in wire number 1. So let's just go back to this. We said that in the steady state, the current flowing, which way is the current flowing, first of all? The electrons are moving from the negative to the positive, so the electrons are moving that way, right? So the electrons moving, number of electrons per second flowing out of wire 2 has got to be equal to the number of electrons per second flowing into wire 1. So we can say I1 is equal to I2. Plug in our relationship between electron current and the drift speed, and we have N1 A1 V1 is equal to N2 A2 V2, right? And the electron densities are the same, right, if it's the same material. But the areas aren't, okay? So we have this inverse relationship, right? If the area of 1 is larger, then its speed has to be smaller. If the area of 2 is smaller, then V2 has to be larger. So V2, or V1 is less than V2, or V2 greater than V1. And sometimes it's helpful to think about an analogy with a water pipe. The water analogy sometimes breaks down with circuits, so you don't want to get too dependent on it. But in this case, it's kind of nice because if you think about just, you have a flow of water in a pipe, and in this case, you just have a fatter pipe, right? So to get the same amount of water flowing past every second, same number of water molecules, they don't have to flow as fast. Whereas in this case, if you have a thinner pipe, right, they have to be moving quicker so that you get the same volume of water to move past every second. It's the same idea here, right? Same idea here. And you can kind of see that with a water nozzle. If you crank if you make it really small, you get a high velocity stream of water, right? So same type of situation here, okay? Just kind of motion of a continuous fluid. It's almost like a fluid. Okay, questions? Let's try another one. In fact, let's just be quantitative about this. Now that we know that the velocities are different, how much different would they be if the area of wire 1 was 4 times bigger than the area of wire 2? Pretty clear. If the area of wire 1 is 4 times greater, let's just go back to here, right? We can just plug this in directly. We can just say A1 is equal to 4 times A2. A2's now cancel out. You have 4 V1 is equal to V2, or V1 is 1/4 of V2. Okay? Directly proportional. What about the electric field? Same situation. What about the size of the electric field in wire 1 versus the electric field in wire 2? All right. So maybe we need a reminder of what the relationship is between the drift speed and the electric field. V is equal to what? U times E. Okay. And so the assumption here is that, again, both wires are made of the same material. So how do the mobilities compare? They're equal. Okay, they're equal. So if we know the relationship between V and V1 and V2, we can say U E1 is equal to 1/4 of U E2, and it's the same U on both sides. So E1 has just got to be 1/4 of E2. Okay, so if the velocities, if the thicker wire has a smaller drift speed, and they both have the same mobility, then it's going to have a smaller electric field because, again, the electric field is proportional to the drift speed in the wire. Okay. Questions? Are we okay there? So answer 2. Answer 2 is correct. Answer 2 is correct. And when you're doing these types of comparisons, again, the thing you want to start with is the node rule. Plug in either this relationship, or now that we have V equals UE, V equals U times E, we could also write this as I, A, U, E, another equation we could use. Plug it into both sides, do the comparison. What are the same on both sides? What's different on both sides? And then just cancel things out. Okay, that's just the simplest way to do it. Okay, different situation. Let's look at 2 wires. Different. We'll assume that the U's are the same. Assume that the mobilities are the same, but different electron densities. And the electron density of wire 1 is 1/3 of the electron density of wire number 2. How do the electric fields compare? Okay. So again, start with the node rule. Plug in the relationship for between the current and the velocity, or in this case, current and the electric field. Cancel out what you know. See what you get. All right, so most of us are saying that electric field E1 is 3 times that of E2. A couple people have the fraction reversed. Let's go through it one more time. You have currents being equal. We know that from the node rule. Steady state conservation of charge. Okay, so we have N1, A1, V1 is equal to N2, A2, V2. The areas, A1 and A2 are same. Okay, they cancel out. And we have N1 be equal to 1/3 of N2. So N1 Just plug that in. 1/3 of N2 times V1 is equal to N2 times V2. So let's look at the drift speeds first. We see that V1 is going to be 3 times that of V2. So what is that saying? It says that you don't have as many electrons per unit volume in this wire as you have in the other wire. Okay, there are just fewer electrons to go around. So in order to get the same rate, in order to get the same number to move by every second, they have to move faster in wire 1 than they do in wire 2. Okay, so if they're moving faster in wire 1, and we know the relationship between V and the electric field, U times E1 is 3 times U E2. You have to have a larger electric field in wire number 1 in order to get them to move faster so that the current stays the same in both wires. Okay? Questions? Okay, this is tricky to think about, but again, if you start from the node rule, that's one of the main things to take away from our study of circuits, is that starting from we'll have another fundamental principle when it comes to circuits, namely the loop rule, or round trip potential, being equal to 0. But for right now, the first one we're dealing with is just the current at any given point in the wire flowing in has got to be equal to the current flowing out in the steady state. All right, let's look at this question. We have go back to our simple circuit that we started with, which is just a single wire. Okay. First of all, directions of the electric fields. Well, we can kind of jumping the gun a little bit, so let's just go back a step. If you have a battery set up like this, we know that the electron current is flowing, we said, out of the negative terminal and into the positive terminal. So that's V. And then because in our model we have an electric field inside a conductor, we have mobile electrons, and therefore there's going to be a force in the opposite direction because the force is equal to the charge times the electric field, which means the electrons are going to move in the opposite direction of the electric field. So we end up with directions for the electric field that point that way. Okay. So the question is, what's the overall pattern of the electric field when we're in the steady state inside the wire? Notice the difference in the magnitudes, so see which one is the best fit. Okay, so almost everybody is saying that pattern 3 is the best fit because all those electric field vectors, how do they compare? Same magnitudes. Okay, they're the same magnitudes. We would expect that because in the steady state, the current should be the same everywhere in that wire, right? And if everything else is the same, N is the same, A is the same, that means V should be the same everywhere in that wire. And then from V equals UE, the electric field should be the same everywhere in that wire. And the electric field's got to point along the direction of the wire to drive the current in that direction, okay, or namely drive the electrons in the opposite direction, okay. But there's something weird here. If I were to draw a battery, I'll assert to you that one way we can think about a battery, and it's not exactly a precise picture, but it's a simple enough model to get us through the day, is that we can think of a battery kind of like two ends of a capacitor. Okay, so the positive end has some positive charge on it, and the negative end has some negative charge on it. And then we can think of it as having some means of driving charge from one plate to the other. And in a sort of a mechanical model, you can imagine turning a crank on a conveyor belt that just brushes up against one plate, drives charge onto the other plate, and maintains that charge separation. Okay, so a battery maintains a charge separation. Of course, in a chemical battery, it's not a conveyor belt, right? But it's some chemical reaction that maintains that charge separation. Well, if that is the case with the battery, what would we expect the electric field of the battery to look like if we have a positive charge on that end, negative charge on the other end? So, for example, the electric field of the battery here would be in what direction? That way, okay. And the electric field of the battery at this point would be that, which way? Same direction, right? Same direction. The electric field of the battery would be what at this location? Opposite direction. What would be the magnitude of the electric field due to the battery be? Compared to those two, those locations which are close to the terminals, we would expect it to be what? We would expect it to be smaller, right? But then we've got a problem, because if the electric field of the battery is smaller here, then the drift speed would be smaller and we wouldn't have a steady state, right? I mean, it's got to be the case that 3 is the correct answer in order to have a steady state. But if we think that the electric field is only due to the battery, we've got a problem. So what we're going to talk about next time is we'll see that the electric field, the net electric field that's driving the current inside those wires, is not just due to the battery. It's not just due to the battery, and we'll talk about that next time.